Hello. This video lecture is about the Riemann integral. We will be dividing this video into three parts. The first part is about the motivation of the study, and the second part will be about the lower Riemann sums and the upper Riemann sums. And finally, for the last part of this video, pag-aaralan natin yung tinatawag na Riemann integral. Well, it looks like the idea of the Riemann integral is not really new to you. In fact, sa mga calculus na courses na na-take up nyo na, pinag-aralan na yung tinatawag nating integral or Riemann integral. Sa subject na to kasi, meron tayong dalawang uri ng integrals na pag-aaralan and we will compare them at the end of the semester. Yung tinatawag nating Riemann integral at yung pangalawa yung improvement, which is what we call as the Lebesgue integral, which is a modern type of integral. Alright, so as we all know, the idea or the concept of integral starts with the following area problem. Suppose you are given a positive continuous function f, which is defined on the closed interval AB. So as graphed, it is the red function as indicated. Ang domain niya ay yung closed interval na AB, tapos positive meaning yung graph niya nasa ibabaw ng x-axis, continuous meaning walang discontinuities na makikita all throughout mula sa A papunta sa B. We ask the following question: what is the area of the region bounded by the graph of f, the vertical lines x equals a, and the vertical line x equals b, and the x-axis? So we would like to find the area of this green region as indicated. You see, manually, the problem is hard because the graph of f may not be maybe curved like this. Now, why would we want to get the area under the graph of a function? For example, for a physicist, if an object is moving along a straight line with a variable velocity f of t at any time t, then the area represents the total distance covered by the object from time t equals a to t equals b. As an example, if let's say this is the velocity versus time graph, if let's say the object is moving along a straight line at a constant velocity, so it looks like this, the graph is like this, right? Why would the area under the graph represents the total distance covered? Because the area, let's say the constant velocity is v0, so this height is v0, so the area under the graph is v0 times b minus a, because what? Because this is just length times height, correct? So why does v0 times b minus a represent the total distance? Because b minus a is the total time elapsed. Right? And of course, v0 is the constant velocity. Well, you know that distance is velocity times time. So v0 times b minus a as indicated. But you see, hindi palaging constant ang speed ng mga gumagalaw na bagay. For example, sasakyan. Your velocity graph may not be a constant function, so it may look like something like this one. So still, the interpretation is the same. Yung area under the graph is still the distance. Okay? For an epidemiologist, for example, these are the people who study epidemics like the COVID-19, right? If the function f of t represents the continuous rate of change of the number of infected individuals at any time t, this could be measured daily or every hour or every week. It depends on the situation. Then the area from t equals a to t equals b represents the total number of infected individuals from time t equals a time t equals b. In this lesson, we wish to extend the notion of area to include functions which may not be continuous at all or which may not be positive at all. In that case, the integral may not really represent an area. And of course, we will study how we can approximate the area. Let's look at this graph. This graph was taken from the Johns Hopkins University Coronavirus Resource Center. Pinapakita nito yung daily reported new cases of COVID-19 in the Philippines. So for example, if we look at this, let's say this vertical bar, no? Parang ganito siya. Really. Like this. Yung width nito represents 1 day, while the total height is the number of infections in that day. Right? So if I calculate the area of this rectangle, number of infection times 1 day, it is equal to the total number of infections that were recorded in that day. So our question is, what does the total area of the rectangles in the graph represent? Of course, we have an answer to that. The total area is the total number of confirmed reported cases of COVID-19 from the start up to the end of the graph. Here I took this yesterday, so as of recording, kapag in-add mo yung area nito, yun yung magsasabi kung ilan na yung COVID-19 cases sa buong Pilipinas. Okay? So to start formally, let us first define what we mean by the word partition of the closed interval. A partition of the closed interval AB is nothing but a finite set of points x0, x1, xn, where n is a natural number, so that x0 is the left endpoint A, x sub n is the right endpoint B, and all the points in this list is strictly increasing, meaning x sub 0, which is A, must be strictly less than x sub 1. X sub 1 must be less than x sub 2, and so on. X sub n minus 1 must be less than x sub n, where x sub n is equal to B. Now, in this case, for each I, whenever you see the symbol delta xi, what I mean by that is the difference x sub I minus x sub I minus 1. As an example, when I say delta x sub 4, it actually meant x sub 4 minus x sub 3. Right? Okay. So this is the real number line, and this is the closed interval from A to B. This is an example of a partition of the closed interval from A to B. You see that it doesn't matter kung hindi pantay-pantay yung distansya ng mga magkakasunod na points. It doesn't matter as long as yung unang point ay magsisimula sa A at yung last point ay matatapos sa B. In this example, ang n na ginamit ko ay 4. And in effect, you see that this set of points divides the interval into 4 sub-intervals. So this is the first, this is the second, this is the third, this is the fourth. So yung delta x of 1 represents the length of the first subinterval. Yung delta x of 2 represents the length of the second subinterval, and so on. Now, sometimes, in order to emphasize, I write P in this manner. I put the word, the name P, then put a colon, and then write this expression. So let us now consider a bounded function f. When we say bounded, it meant to say that if this is your function f, when we say that f is bounded, we meant that the range is bounded. So in this case, yung range niya yung portion na ito ng y-axis, right? When this the function is bounded, this set is bounded from above and below. So meron kang upper bound, meron kang lower bound. So it meant to say that the values of f do not blow up to infinity or negative infinity. Now, we will define the following notations. They may be intimidating at first, but you will see that they are natural. Para sa bawat sub-interval na I, sub-interval ng partition, meron tayong little mi, tsaka capital Mi. Now, yung f at p, you can ignore them. This is just to indicate na yung value niya ay nakadepende sa kung ano yung given na f at kung ano yung partition na p. So, pag pinalitan mo yung partition, nag-iiba yung value na ito. Pag pinalitan mo yung function, mag-iiba ulit yung value na itong dalawa. Now, ano yung mi tsaka fi? For you to imagine this, I want you to look at, pag sinabing m sub I, titignan mo yung I na sub-interval. Ito yung pang-I na putol. Sa pang-I na putol, titignan mo yung mga values ng f. Siyempre, marami yun. Iba-iba. Depende kung paano nagbe-behave yung f. Now, among the values, kukunin mo yung infimum. Kung continuous naman yung f, the extreme value theorem will guarantee that the infimum is just the minimum. Right? Similarly, yung big M naman, big Mi, pupunta ka ulit dun sa I interval, and then you will look at the values of f on that interval, and then among those values, kukunin mo naman yung supremum. Again, kung continuous naman si f, yung supremum na yan, siya rin yung maximum. And then, meron tayong dalawang bagong terms. Meron tayong L, meron tayong capital U, capital L. L stands for the lower Riemann sum. U stands for the upper Riemann sum. So first, let's ignore this summation. First, let's concentrate here. So in order to get LFP, you will be needing the little mi's. Yung bawat mi, i-multiply mo sa delta xi. So, I think I need to illustrate. So, for example, this is the x-axis, and let's say this is the function. Let us say, ito yung x sub I minus 1, at ito naman yung x sub I. So, basically, we are looking on this interval only. Of course, on this interval, ang titignan natin yung behavior ng function sa loob ng interval na yan. Okay? So, for example, in this case, kung saan nakaka-reach ng sabihin na lang natin dahil continuous naman yung function, kung saan nakaka-reach yung function ng pinakamababang value, doon nagaganap yung little mi. In fact, yung height na ito, for example, dito sa interval na ito yung m sub I. Kasi sa interval na ito yung pinakamaliit na value ng f. In this case, on the other hand, ito naman yung capital M sub I kasi yan naman yung pinakamalaking value ng f sa buong interval na to. Notice that little mi and big mi may be achieved in the middle. It depends on how the function behave. Now, going back here, yung mi, i-multiply mo sa delta xi. So, for example, yung little mi ay ito, yung delta xi ay ito. So, if you multiply them, what will you get? It's like multiplying width times height. So, therefore, we are actually getting this area. Right? On the other hand, doon naman sa upper sum, kino-consider natin yung big mi. So, your rectangle will be a lot taller. So, for the lower Riemann sum, yung mga rectangles na yun, yung mga area ng mga rectangles na yan, i-add mo I from 1 up to n. Meaning to say, gagawin mo to sa lahat ng sub-interval, yung mga area na makukuha mo, i-add mo lahat. Okay, as an illustration, we have the following figure. So, nakikita nyo, doon sa LFP, as indicated here, yung mga rectangles mo are under the graph of f. Kasi ang kinuha natin, halimbawa sa interval na to, yung pinakamaliit na value ng f, ito yung ginagamit na height. Sa interval na ito yung pinakamaliit na value ng f. Sa interval na ito, you see, ang pinakamaliit na value ng f ay ito. Kaya yun yung ginamit na height. Pero sa interval na to, ang pinakamaliit na value ng f ay ito. Kaya yun yung ginamit na height ng rectangle. So, as you can see, yung LFP is, you can say that this is an underestimation of the area. Because parang kulang siya to properly compute the area under the curve. On the other hand, ang UFP naman, ito naman yung mga rectangles that circumscribe the graph as indicated in the picture. So, this is an overestimation. Okay? So, as you can see, dito sa first interval, ang pinakamalaking value ng f ay ito, kaya siya ginamit na height ng rectangle. Sa second interval, ang pinakamataas na value ng f ay ito, kaya yung gagamiting height ng rectangle. Sa third interval, ang pinakamalaki ay ito, kaya yung ginamit. And finally, sa last na sub-interval, ang pinakamataas na value ng f ay ito, kaya yun yung ginamit na height ng rectangle. Now, in our discussions, we are interested normally, or we will be interested with how these two sums differ from one another. Of course, laging mas malaki yung u kesa sa L kasi nga ito yung mga supremum, ito yung mga infimum. So, we would like to know their difference. So, in this case, ito yung u minus L. In picture, yung u minus L, so parang binura mo yung portion ng L doon sa portion ng u. Do you get that? Okay? So, let us have some example. So, let f of x be x squared. So, ito yung usual na quadratic function. But, we will restrict the domain from 0 to 1. Let us consider the partition P with points 0, 1/4, 3/4, and 1. Now, I want you to calculate the lower Riemann sum, the upper Riemann sum, and the difference between the two sums, the upper and the lower sums. Now, in order to facilitate the calculation, I prepared this table for you. Sa table na to, nandito yung mga delta xi na kailangan. Lalagay mo dito. Now, bakit yung I natin nagre-range from 1 to 3? Kasi yung partition natin merong 4 na points. So, therefore, hinahati niya yung buong interval into 3 parts. Okay? Ayan. Ito sa picture. 1, 2, 3, 4. Pero yung number of divisions mo ay 3. Okay? So, kailangan natin yung little mi tsaka yung big mi. How do we calculate delta xi? For example, delta x1. In order to do this, we will subtract 1/4 minus 0. So 1/4 minus 0 is 1/4. Next, delta x2 is 3/4 minus 1/4. What's 3/4 minus 1/4? What is this? That is 1/2. Then finally 1 minus 3/4, again that's 1/4. Okay? Now how do we calculate the little mi's? So ang gagawin mo, titignan mo yung bawat sub-interval. So for example, sa first sub-interval, ano yung pinakamaliit na value ng f? So as you can see, dahil yung function natin ay strictly increasing, yung pinakamaliit na value laging nangyayari sa pinakakaliwang or sa leftmost point in the interval. So in this case, sa 0. Ang value ng f sa 0 ay 0, so ito ay 0. Right? Sa second subinterval, dahil nga strictly increasing yung function natin, yung smallest value niya is achieved on the left endpoint. So doon sa 1/4. The question is, what is this height? So that height should be the value of f at 1/4. Ano ba yung f of 1/4? According to the formula, that's 1/16. Kaya ito dapat 1/16, right? At yung pangatlo, sa third na subinterval, the infimum will be achieved at the left end point 3/4. So if you take f of 3/4, you will get 9/16. Like 9/16. So ayan. Okay. On the other hand, again, dahil yung function natin ay strictly increasing on the interval from 0 to 1, yung supremum naman natin, or in this case, maximum kasi continuous yung function, yung supremum natin ay ma-achieve naman sa right endpoint. So, for example, sa first subinterval, it can be achieved at the point 1/4. So, f of 1/4 is 1/16. Ilalagay mo dito 1/16. Okay? Sa second subinterval, ang right endpoint ay 3/4. F of 3/4 is 9/16. Sorry. And last but not the least, doon sa last na endpoint natin, last na interval natin, ang right endpoint ay 4/4 or 1. F of 1 is 1. So, lalagay mo dito ay 1. Sorry. Okay? So, how do we calculate the lower Riemann sum, or the L? In order to calculate the L, what we do, we will multiply the little mi with the corresponding delta xi, yung product nila, product nito, i-add mo lang lahat. As shown. So, ito yung 0 times 1/4, 1/16 times 1/2, ito yun. 9/16 times 1/4, ito yun. So, if you add all of them, you'll get the sum 11/64 or 0.171875. In pictures, ito yung mga lower rectangles mo, no? So, you see yung unang rectangle natin, walang height at all kasi nga yung mi mo ay 0. For the upper sum, ito naman yung big mi instead of little. 1/16 times 1/4, 9/16 times 1/2, 1 times 1/4. So all in all, that's 35/64, and the sum is 0.546875. Now the easiest to get is the difference, kasi at this moment na-compute mo na yung u tsaka yung l. So isasubtract ko lang, I see that u minus l is 0.375. So in the picture, ito yun. Okay, so let us consider the same function, but this time using a different partition. So in this case, yung partition natin is almost the same, except nag-insert ako ng 1/2 doon sa gitna ng 1/4 at saka ng 3/4. So therefore, dahil nag-insert ako ng one more point, yung I natin madadagdagan from 3 magiging 4. Okay, so your table will be a lot wider. Yung partitions natin dumami, di ba? Okay, so in this case, yung mga delta xi mo are all 1/4 in length. Ang tawag natin dito regular partition. Regular kasi pantay-pantay yung pagkakahati ng bawat sub-interval, kaya 1/4. 1 kasi yung length ng buong interval divided by 4, so tigo 1/4 sila. Now similarly, in order to get the mi, dahil yung function nga natin ay increasing on the entire interval from 0 to 1, the little mi or the infimum can be obtained on the left endpoint. So evaluate mo lang si f sa bawat left endpoint. Okay, ito yung lalabas na values. F of 0 is 0, f of 1/4 1/16, f of 1/2 is 1/4, f of 3/4 is 9/16. Similarly, yung big mi naman, yun yung yung mga values ni f sa right endpoints, kasi nga increasing yung function natin and continuous. F of 1/4 is 1/16, f of 1/2 is 1/4, f of 3/4 is 9/16, f of 1 is 1. So, to calculate L, mamultiply lang ulit natin ito, little mi with the delta xi, mi delta xi, mi delta xi, and so on. Then, i-add natin lahat. As a result, ito yung nangyari. Okay? Yung upper sum naman natin, ito yung nangyari. And yung difference na u minus L ay ito. Now, what is the point of all of this? Well, it is because I want you to compare the L, the U, and the U minus L for two different partitions. One being finer than the other. Kapag sinabing finer, meron siyang more points than the other one. Well, let's compare. So for the first or the original partition, the lower sum is around 0.171875. Tapos, yung bagong lower sum is around 0.21875. So which one is larger? Of course, the lower sum of the new partition. For the upper sum, ano naman ang nangyari? You see that the value of the upper sum decreased, right? And as a consequence, ito naman ay consequence lang. Yung lower sum mo kasi tumaas, yung upper sum mo bumaba, so yung difference nila ay liliit. So from 0.375, naging 0.25. So yung again, yung lower ay lumaki, yung upper ay lumiit. Of course, yung difference nila ay liliit. This is actually a particular case of a more general result. Okay, so let's say f is a bounded function defined on the interval from a to b. Let's say you have two partitions, p and p star, of the closed interval from A to B, where P is a subset of P star. What does that mean? It meant to say that all the points in P are in P star, and possibly there are points in P star which are new to P, or not yet in P. So in this case, the lower sum for the new partition with respect to the new partition will be at least the lower sum of the function with respect to the old partition. On the other hand, yung upper sum naman ay liliit, and yung difference na yan ay liliit. So again, yung lower sum ay lumalaki kapag nagdadagdag tayo ng points in the partition. Ang upper sum ay lumiliit kapag nagdadagdag tayo ng mga points in the partition. So you may ask, sir, kapag ba nagdagdag ng maraming points, let's say I add points one by one and then tuloy-tuloy, palaki lang ba ng palaki yung L? Pwede ba makaabot sa infinity? Gaya ng U. Papaliit lang ba ng papaliit yung U? Pwede ba makarating ng negative infinity? So you might wonder. The question is no. So we will see. So in the following, let us denote by P script P A B to be the set of all partitions that we can make from A to B. We have the following theorem. If f is a bounded function, you know that the range has a lower bound and an upper bound. So let M represent a lower bound and big M represents an upper bound. Then for any partition P that you can make from A to B, this number M times B minus A is always a lower bound for all the lower sums. On the other hand, yung big M times B minus A is always an upper bound for all the possible upper sums. Of course, the lower sum will be, this is trivial, right? So it meant to say that even though yung LFP ay papalaki habang dinadagdagan mo yung points in the partition, kahit na papalaki yung L, diba? Kapag nagdadagdag ng points, hindi siya makakaabot ng infinity kasi it's always bounded above by this number, big M times B minus A. Similarly, kahit na yung U natin, yung upper sum ay papaliit habang nagtatagdag ka ng points in the partition, hindi naman siya makakaabot ng negative infinity because always it will be bounded below by MBA. Now, question is, what are these numbers? You can look at this picture if you want. So again, yung little m siya yung lower bound ni F, yung big M siya naman yung upper bound ni F. Yung little m times B minus A is actually the area of this rectangle, the blue rectangle, right? Yung big M times B minus A siya naman yung area ng green na rectangle. So as you can see, if we construct any partition here, yung lower sum mo, ito, right? Ito yung lower sum natin, will be bounded below by this. Yung upper sum mo naman, ito ganyan, will be bounded above by M times B minus A. As a conclusion, for any bounded function f, so long as f is a bounded function, the set of all possible values of lower sums, or the set of all lower sums with respect to any partition, is always a bounded set. Similarly, the set of all upper sums is also a bounded set. Actually, what's important is that the set of all lower sums is bounded above. And the set of all upper sums is bounded below. Kasi yung lower sums lumalaki na lumalaki. Yung upper sums ay lumiliit na lumiliit. Does this ring a bell to you? Naalala nyo yung tinatawag nating monotone convergence theorem? That if you have an increasing sequence of numbers and then this increasing sequence has an upper bound, automatic na siya ay may limit. Similarly, if you have a decreasing sequence of real numbers, tapos yung sequence na to ay may lower bound, then automatic na yung sequence na yun ay may limit. We call it as the monotone convergence theorem. But you see, the monotone convergence theorem is just equivalent to the completeness axiom, which states that if a set of numbers is a bounded set, automatic meron siyang supremum at saka infimum. This is why we have the following definition. So if you have a bounded function f, the upper Riemann integral, so meron tayong bagong term, the upper integral or the upper Riemann integral of f from a to b is defined as the infimum of all the upper sums with respect to any partition. Kasi nga, ang nangyayari kapag nagdadagdag ng points in the partition, yung upper sums mo lumiliit na lumiliit, but hindi naman siya masyadong liliit kasi the infimum is guaranteed to exist by the completeness axiom. So yung infimum na yun is what we call as the upper integral or the upper Riemann integral. Similarly, yung lower Riemann integral naman from a to b ni f is defined as the supremum of the lower sums. Ito yung mga lower rectangles mo. So ano kayong pinakamalaking possible sum? Actually, hindi ito pinakamalaki because it cannot be, sometimes it cannot be achieved, but the supremum can exist. Now, this leads us to the definition of the word integrable. So we say that f is Riemann integrable on the interval AB if these two values above agree with one another. So pag nag-equal sila, that's the time we can say that f is Riemann integrable. Kung hindi, syempre hindi. Now, as you will see, for most of the interesting cases, these two are equal, so most likely, integrable ang isang function. Pero, makikita nyo mamaya, meron tayong mga examples ng functions na hindi integrable, where the upper integral and the lower integral do not agree. In this case, the common value of u and f and l, is what we call as the Riemann integral of f over ab. So, kung saan man nag-agree yung dalawa, yun yung tinatawag nating integral. F from a to b. Siya yung sinusulat natin sa calculus noon as the integral from a to b ng f. Okay? So, let's look at some example. By the way, before examples, let's give the following remarks. So, given a bounded function f, similar to what we have discussed earlier, kung si f ay bounded below by m, above by big M, then yung lower sum, hindi naman yan lalaki sa upper sum, never, no? Right? Kasi nanggaling to sa ilalim, ito nanggaling sa ibabaw. So, hindi sila pwedeng mag-cross ng landas. Similarly, the lower integral cannot go below this value. The upper integral cannot go above this, beyond this value. Ito ulit yung dalawang rectangles nating malaki. Therefore, kung ito ay totoo by default, di ba? Kung gusto mo mag-equal sila, you don't need to show this because this will hold for any bounded function. So if you want to prove that a function is Riemann integrable, all you have to do, or all you have to prove is that yung lower integral mo should be at least the upper integral. Because if this is true, and if this is true, Together, they will imply that the L and the U are equal. So let's consider this example. So if f is constant, say, ang constant value niya ay c, on the interval from a to b, how does it look like? It looks like this. So ito yung a, b, ito yung constant function mo, no? C ito. Then, automatic si f ay Riemann integrable, and ang kanyang integral ay equal to c times b minus a. As you can see, bakit c times b minus a? Kasi area lang naman siya nito eh. This is c times b minus a. Ito yung b minus a. Ito yung c. So for the proof, we are going to use our definition. Alam ko meron na kayong mga formulas nyo sa calculus noon. But in fact, yun nga yung point. Yung mga details na hindi nyo pinag-aralan noon nung nasa calculus kayo, ngayon natin pag-aaralan. So let's consider the partition P. Let's consider any partition P from A to B. So this is an arbitrary partition, right? Dahil nga yung function mo ay constant, ang value niya palaging C, ang infimum mo, tsaka yung supremum mo sa bawat sub-interval will always be C. Therefore, if you will compute the upper sum, ito yung formula niya, ito ay palaging C. C times delta xi. Using properties of summation, I can bring out the C, or I can factor it out. Then, pag inad ko yung length ng bawat sub-interval I from 1 to n, of course, I will just get the length of the entire interval, which is b minus a. Diba? Kung ito yung interval mo, ito yung delta, let's say, ito yung delta x1, ito yung delta x2, delta x3, delta x4. Pag inad ko lahat to, ang lalabas lang yung interval mo from A to B. Similarly, if we calculate the lower sum, C lang naman din ito, so that leads to the same result. Because P is arbitrary, it means to say that these formulas hold for any partition P, then yung infimum ng mga upper sums, dahil pare-parehas, C times B minus A will be C times B minus A. Similarly, yung supremum ng mga lower sums, isa lang naman ang possible na lower sum, is also C times B minus A. Kasi diba kapag ang set mo singleton, let's say A lang ang laman, ang supremum niyan ay A. Kung isa lang naman din ang laman ng set mo, ang infimum niya rin ay A. Therefore, by definition, f is integrable on AB, and that the common value C times B minus A should be the value of the integral. Okay? So this is the easiest example. Let's consider a more complicated one. So now, let's consider the function which we have considered a while ago, yung f of x equals x squared. Let us prove that this function is Riemann integrable on the interval from 0 to 1, and let's find out kung ano yung integral ng f from 0 to 1. So this is the trick. Of course, the proof is not simple, and dahan-dahan. Sundan natin, dahan-dahan. Okay? So what I do is magde-define ako ng maraming partition. P1, P2, P3, P4, and so on. Pn. For each n, tawagin natin Pn yung partition na ito. Kaya nga sabi ko kanina, itong partition na ito, ang tawag dito ay regular partition. Why is this called a regular partition? Kasi yung bawat interval mo, let's say yung P4, 0, 1/4, 2/4, 3/4, 4/4. Yung interval mo from 0 to 1 ay nahati sa 4 equal parts. Pare-pare sila, ang length ay 1/n. Okay? note that for Pn, delta xi is 1 over n. Evidently, no? If you subtract 1 over n minus 0, 1 over n, 2 over n minus 1 over n, 1 over n, and so on. Again, because f is increasing on the closed interval from 0 to 1, then on the ith subinterval, the infimum can be obtained by evaluating f on the left endpoint. Bakit ganito yung left endpoint? I think there's an error here. This should be n, wala yun. Kasi yung first, for example, yung first subinterval mo 0, 1 over n. Yung second 1 over n, 2 over n, right? And so on. Pag ikaw nasa ith na, ay tsura ng ith subinterval mo ay, kasi yung second, ito yung I, no? So, ito yung I over n, I minus 1 over n. So, i-evaluate din mo si f doon sa left endpoint. So, ang definition ng f of x equals x squared. So, i-square mo lang ito. Ito siya. Then, simplifying, yung lalabas. In a similar fashion, yung big M mo naman, ma-obtain mo by evaluating f on the right endpoint, which is I over n. Because f of x equals x squared, f of I over n is I squared over n squared. Did you follow? You can pause this video if you want, ha? If you want to have some time to catch up. Now, meron tayong mga formulas na gagamitin in order to facilitate the calculation of L and U. Yung una yung summation ng I from 1 to n. Ito yung 1 plus 2 plus 3 plus 4. Naalala nyo ba to? Okay, binigay ko na yung formula para sa inyo. Ito naman yung sum ng mga first n squares. Ito yung formula. Kailangan alam natin sila. We can compute the L, the lower Riemann sum as follows. Ito yung formula niya, no? Ito yung kinalculate ko kanina. In delta xi ay 1 over n. And then, see, what I do is, you can see this factor. This factor, 1 over n cube, is independent of I. I kasi yung index natin, pero siya ay n. So, parang pwede mo siyang ilabas. Magkakaroon ka ng 1 over n cube dito. Tapos, using the properties of summation, summation of I squared, dito nang galing yun. Yung 2 summation of I, dito nang galing yun. Summation ng 1, dito nang galing yun. Now, evaluating these summations using these formulas, ito yun. Tapos yung sum ng mga 1, I from 1 to n, uulit lang, nauulit si 1 ng n times, kaya ito ay n. Then using algebra, you can simplify it as follows. So you see it's very complicated, no? How about for the u? The u is calculated similarly. Ito yung u. Ito yung formula niya. Ito yung value ng big M na na-calculate natin kanina. And of course, yung delta xi ay 1 over n. Again, yung 1 over n cube ay constant with respect to this summation. So you can bring that out. May 1 nito. And using the formula written a while ago, ito siya. And simplifying ito. So, ang difference ng L at saka sa U ay yung sign na ito. Sa U, plus yan. Sa L, minus. Notice that. Oh, dahil nga yung L, F, ito yung lower integral, ay supremo ng mga L. Lagi siyang mas malaki sa lahat ng lower sums. Similarly, yung upper integral mo naman ay infimum ng mga upper sums. So, lagi siyang mas maliit sa kahit na anong upper sum. Then, the following can be derived using algebra, no? Ang u minus f, yung difference na ito, of course greater than or equal to 0 because u is always bigger than L, will not exceed the difference between, you can imagine it like this, parang ito yung gitna, ito yung integral, parang ito yung integral, imagine niyo ito yung u, ito yung L, ito yung u, FP, ito yung L, FP. So parang yung difference na ito mas malaki kaysa sa difference na itong dalawa. You can imagine it that way. Anyway, let's continue. So, saan nga ba equal ito? Itong dalawa. Gagawin ko, isusubtract ko ito minus ito. So what we have is 1 over n as a difference. Now, ito yung inequality, no? Now, we have this inequality. I-shade ko or i-highlight ko, no? Ito yung mahalaga dyan. Parang yung number na ito ay nasa pagitan ng 1 over n tsaka ng 0 kahit na ano yung n. So, if you let n approach infinity, yung 1 over n ay nagpupunta ng 0, diba? May ipit ngayon sa gitna ito. That's why, that means that this number should actually be 0. Hence, equal yung upper sum tsaka yung lower sum. And that f is Riemann integrable. Okay? Finally, if you want to know the integral, you can take the lower integral or the upper integral. Kahit alin doon mag-work. In this case, kinuha ko yung upper integral. It is the infimum of all the upper sums. But among the upper sums, it is interesting to note yung UFPN. Ito yung UFPN. No? And then the infimum can be obtained by setting n to infinity, because if you make regular partitions and you let n approach infinity, paliit ng paliit yung mga width ng mga rectangles natin, which is what we like. So when you take the limit is 1/3. So yung integral na to ay 1/3. Nagmamatch ba siya dun sa integral na alam nyo? Yes, actually later ipoprove natin that the formula that you know actually works. Finally, let's consider this example. If nasa advanced calculus kayo noon, napag-aralan nyo dapat itong very important function na ito, yung tinatawag nating Dirichlet function or Dirichlet function. Babasahin siyang Dirichlet kung kayo nasa Germany, pero Dirichlet kung kayo nasa France. So, ang definition ng Dirichlet function is weird, no? 1 ang value niya kung si x ay rational. 0 naman kung si x ay rational. Sa example na to, meron tayong dalawang facts na gagamitin. Tinatawag nating density property for the rationals and irrational. Dapat alam nyo na sa gitna ng kahit anong dalawang real number ay may rational. At sa gitna ng kahit na anong dalawang real number, laging meron ding irrational. This is our first example of a function that is not Riemann integrable on any closed interval. To see this, let's pick an arbitrary closed interval AB where A is less than B, and let's pick an arbitrary partition P of the closed interval AB. Because every interval contains a rational number, sa bawat sub-interval, yung function mo na ito will get to have a value of 1. Kasi nga, laging may rational number sa gitna ng kahit. So kahit paano mo putol-putulin yung interval mo, laging may sisingit na rational number sa gitna ng bawat isa. Dalawa lang naman ang value ng function mo, 0 or 1. So, laging sa gitna ng kahit anong interval, magsi-0 at mag-1 ka. Kaya yung supremum mo ay 1 sa bawat sub-interval. And of course, dahil naman sa bawat interval may irrational number din, yung function mo magre-reach palagi ng value na 0 sa interval na yan. So, it will always achieve a value of 0. So, ang infimum mo ay 0. Dalawa lang naman, 0 and 1. Ano yung infimum ng set na yun? 0 for all I. So, yung big M natin ay 1 palagi. Yung small m natin ay 0 palagi. As a consequence, when we calculate the upper Riemann sum of D with respect to any partition, ito yung lalabas. Yung big M kasi natin ay 1. Mangyari, add mo na lang lahat ng mga delta xi. Ang sum niyan ulit, yung length lang ng buong interval. At yung lower Riemann sum mo naman ay ma-obtain as follows. Yung 0 dito siya kasi yung little mi. Right? This is always 0, kaya ito ay 0. Because this is true for an arbitrary partition P, ibig sabihin yung supremum mo, again, yung set of all upper sums mo, isa lang ang value, B minus I. At yung set of all lower Riemann sum mo ay 0 lang din ang value. Kahit na ano yung partition. So, yung upper integral mo, which is the infimum of all of this, is B minus A. At yung lower integral mo ay laging 0. And you know that because A is less than B, B minus A is positive, it cannot be equal to 0. So, dahil nga yung U of T ay hindi pareha sa L of D, si D ay hindi Riemann integrable. Okay? So, in the next lesson, we shall give more examples and other equivalent formulations for a function to become Riemann integrable. Kasi nga, as you can see, it is quite hard to determine by definition if a given function is integrable or not. So, we would like to make the test easier and as much as possible give more examples. Okay? Till next time.